Okay, we've looked at this before. It's the Greek letter sigma.
Yes.
Okay, so have your calculators handy. I'd lend you out one, but mine has gotten legs and just walks. You need that back. No, T would put it back here and I took it downstairs. It's somewhere downstairs. So if you see these green tape on one, that's mine. Just get it back here. It's used to express a sum in abbreviated form. Plus, we're going to use sigma notation, but I'm also going to introduce you to a kind of tricky process that you're going to have to do in calc next year in terms of finding infinite sum of rectangles to get the area of the curve. Okay? One of the other big applications. Okay. There's more details on sigma notation. You have a lower limit of summation and upper limit of summation, and you indicate your index. You have to have a variable associated inside here. Okay? Put the chemistry away. Put the chemistry and anything else away. This is your note-taking time. Okay? Be a little more flexible during the group time if you want to work on the chemistry, but not now. Okay. So summation from k equals 100 to k squared. What does that mean? So it's 1 squared, plus 2 squared, plus 3 squared, plus dot, 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 plus 100 squared. Now that'd be kind of laborious to add that all up. Could we use our S sub n formulas? Yeah. Which one? Is it geometric? No. Is it arithmetic? No. So, no, there are no formulas you memorize to do this one. Can we try it on the TI-89? 1 or 2?
Yes.
Go. Let's try it. We'll get on the TI-89.
X squared.
Use your sum symbol. K squared, comma K, going from 1 to 100. It's pretty straightforward.
338350.
Really?
Yeah.
Yes.
That's huge. We're going to do this by hand in a second. I'm actually going to memorize the formula for the sum of the first n squares. Okay. Where's Emma? Oh.
She's not here. She's
No, but she would have told us when's the best time to get this memorized. Now! Tonight! Not sometime on the beach. Okay, from 1 to 5 of negative a half to the n. So that's negative half to the first, plus negative a half squared, plus negative a half to the third, plus negative a half to the fourth, plus negative a half to the fifth. So you get negative 1/2. It's a pi. It's close. Negative a half, positive a fourth, negative an eighth, positive a 16th, negative a 32nd. Now, what's going to be faster at this point? Yeah, probably just add them up because, yeah, you're out, probably recognize as geometric. We could use our S sub n formula for geometric. But you can get these all in 30 seconds, right? Negative 16 plus 8 plus negative 4 plus 2 plus negative 1, 30 seconds. How does that work out? Negative 21 and 10, negative 11. Negative 11, 30 seconds. So let's check it. Check with the TI-89.
It is negative 11.
It is? Okay. That's sum. Left parentheses negative 1 divided by 2. Raised to the n going from 1 to 5. Okay. Uh-oh. Infinity symbol. And be careful, before you say 1, look carefully where the first term is. It's a half to the 0 plus a half to the first plus a half to the second. So you get 1 plus a half plus a fourth. So it's geometric, common ratio of a half, but first term of 1. So the infinite sum is t sub 1 over 1 minus r. 1 over 1 minus a half, and you do get 2. And you can check that on your 89s too, using the infinity symbol for that last argument. Okay. Now here's some properties of finite sums. Can be distributed. Because this is saying our first term is going to be A1 plus B1. Plus, now I'm going to put I equals 2 in to get A2 plus B2. Plus, and then A3 plus B3. And then we're going to end with AN plus BN. You see how we could rearrange that? And put all the A's together first. A1 plus A2 plus A3 up to AN. And what's going to be the summand for that? Not A. No. 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 Look, a summand usually has the index variable inside it. That's how you make it change. So A sub I. A sub I.
Oh, I thought that was A sub 1.
Hardly. That's an I there. How is that going to change if that's a 1? Then it's just the constant sequence of A1 plus B1, A1 plus B1, A1 plus B1. Plus B sub I. So you can distribute summation over addition. Can you distribute over a multiplication now?
Yes.
Gotta be careful here. You can just pull out the constant. Because this is going to be C times A sub 1 plus C times A sub 2 plus C times A sub 3 all the way up to C times A sub n. And you factor the C out of that. Plus A3 plus all the way up to A sub n. So it's C times summation from I equals 1 to n of A sub I. So summation is a lot different than limits. Remember, we're pretty flexible with limits, about distributing them over addition, subtraction, division, and so forth. But not so on summation. Because if you think about this, what if it was A sub I times B sub I? What do you want to do with that? Summation from I equals 1 to n of A sub I times B sub I. Well, no, but this isn't a constant now. Can I just multiply the 2 from I equals 1 to n?
That would make sense.
I equals 1 to n, okay? Well, this is A1, B1 plus A2, B2, etc., right? Up to AN, BN. But this is A1 plus A2 plus A3 up to AN times B1 plus B2 plus B3. Now, do you see the problem? This is no simple FOIL. This is n terms by n terms. How many terms do you get? N squared. You're going to get an A1 times B1 term, but you're also going to get an A1 times B2 term. And that's not mentioned here at all. So this is a big, big, big no. You can't go there. That's why our list looks kind of limited. These properties of finite sums. You can't just distribute over anything you want. And this comes up again when we do the integral too. The integral symbol. You'll be able to take a constant multiplier outside of the integral. That's it. Here.
So for that question, would you just put it in your calculator? Like
If it was something like that, yeah. But as you can see, what we're going to do if we have like an x squared or something like that, that comes up next. There are some formulas I want you to memorize. Commit these formulas to memory. They're special series. They're key for understanding the integral in calculus. Now, this one you already know, the sum of the first k integers. These are called the triangular numbers.
Oh, yeah. That's my problem. Where you make the triangle things and you add all the dots.
Right, you can go like this. 1, 3, 6, 10 pins.
15.
Former bowling cap of the world, Milwaukee. Billiards, right? 1, 3, 6, 10, 15. These are called the triangle numbers because you have a triangular array of dots and look at their sum. It's also the series 1 plus 2 plus 3 plus plus n, which is arithmetic. The first term is 1. The nth term is n because it is the identity sequence. So that's why you have to be careful. This is one of those rare cases where t sub n and n are the same. And so the sum of the first n terms is normally t sub 1 times 1 plus, I'm sorry, no. Help me out, my sum of the first n terms formula for arithmetic. No. Well, yeah, you can have that in there. What else do we need? Okay. How do you memorize these formulas? You practice using them over and over again, okay? You can't be that fuzzy. Right? It's got to be crisp and there. A number of terms of n. The first term, the nth term, n. So that's a special formula. N times n plus 1 over 2. Sum of the first 100 numbers, 100 times 101 over 2. 50 times 101, 50, 50. That's what we did the first time.
Could you distribute the n on top and the...
I would accept this as the formula 2n squared plus n over 2. Okay. We're also going to see that it's part of Pascal's triangle. This is one of the diagonals in Pascal's triangle. We'll look for it again later in chapter 15. Okay, the sum of the squares. I'm not going to prove these for you now, but they're coming up later. The sum of the cubes, we're going to prove it in the next section, actually. The sum of the cubes looks a lot like this, but it's n squared times n plus 1 squared over 4. So if you got this one down, just remember that the sum of cubes is the square of that, the answer. And the hardest one to remember perhaps is this one. But it starts off like the other one, n times n plus 1 times 2n plus 1 all over 6. Okay, so you'll see the logic and why it's that when we do our section on inductive proofs, okay? But let's just check these formulas right now and see how they work. So we'll prove them in the next section, but for now let's check some examples. What's the sum of the first 4 squares? Well, in this case, it's easy enough not to use the formula. So let's use the brute force technique here.
30.
You'd have 1 squared and 2 squared and 3 squared and 4 squared. You have 1 and 4 and 9 and 16. 30. Right. Now we look at the finesse technique. There. What am I doing? My circumflexes or whatever you want to call them. Finesse. Finesse is, I memorized a formula for this. Right?
Yeah.
Which was n times n plus 1 times 2n plus 1 over 6. Now what does n refer to here?
The thing on the top.
The 4, the upper limit. Okay? So n equals 4. So we get 4 times 5 times 9 over 6. Or in the vernacular, 45. And that'd be wrong. Now, hang on. Hang on. I think... No, it's right.
It's right, your math is wrong.
My math is very wrong.
It's 20 times 9, which is 180 divided by 6
Yeah.
is 30.
It's 30. It's 30. Okay, thank you. I thought for a second you were the wrong formula. That really bad things. All right, let's try brute force again now in the sum of cubes.
1, 8, 27, 81.
No.
64.
64. There we go.
I was thinking 3 to the 4.
9, 36. 100. Oh, isn't that cool? Exactly 100. Now we try the finesse technique with a memorized formula. So it's n squared times n plus 1 squared all over 4. Or 4 squared times 5 squared over 100.
What? No.
It's over 4.
In some circles. And we get 100 again.
Yay.
Now, you might say in either case, brute force was a little faster, but we only looked at 4 terms. Your formula is going to be much faster. Okay. Let's check it on that one we did before. Remember this one? Where was that one from back here? Where'd it go? Yeah. Sum of the first 100 squares. Now by formula, here's our finesse technique now. In this case, n will be, that's right. In this case, n will be 100, so we get 100 times 101 times 201 all over 6. And this amazes me too, because divided by 6 can sometimes create, fractions. But it never will in this case because, for some strange reason, because if we're always adding up squares of integral numbers, how can you have a fraction? Yeah, because we can get the 3 into the 201 and the 2 into the 100 and so forth. On your calculator now, what do you get? Checks out? 338350. Okay. Now, the reason we have you do this is because you're going to be summing up the rectangles that estimate the area under a curve. Now, how can that possibly give us the exact area? Because those rectangles are missing the curve, right? So what do you do if you don't like your estimate? Make smaller rectangles. Right?
Yeah.
And then those smaller rectangles will be able to fit the curve better. They still won't be perfect though, right? So we let that process go ad infinitum. And keep on making the rectangles smaller, which means you have to add more and more and more rectangles. And so your n up here is approaching infinity. So we want you to know those formulas so you can see the process of how when we look at the limit as we approach infinity and have an infinite number of rectangles, all infinitesimally small, that they will sum up to the exact area. And that in a nutshell is integral calculus. Okay. We won't get to it this year, but we want you to have the tools to be able to simplify algebraically some of the expressions and limits you're going to do next year. Well, hello, here it is. Express it in sigma notation and evaluate. So yeah, this is a tricky one because, it's the product of two things all the way down the line, right? Right, so we could look at the first sequence and the second sequence, right? The first number?
I was thinking, could you start doing like a sigma thing like this by finding T sub n and then putting your equation for T sub n into the sigma?
Right, but then you're going to have to have both, right? You want a formula for the nth term, but it's going to help if we just multiply this out and go 2, 12, 30. I don't think you're going to recognize that. That's neither arithmetic nor geometric.
No.
So, but you recognize the 1, 2, 3 sequence, 1, 3, 5 up to 199. That's arithmetic. With a first term of 1 and a common difference of 2. And so we have T sub n equals T sub 1 plus n minus 1 times d. We don't know the number of terms. So 199 equals the first term 1 plus n minus 1 times the common difference of 2. 198 equals n minus 1 times 2. Divide 99 equals n minus 1, so n equals 100. I think we would have found that when we do the second part, the 2, 4, 6, up to 200, I think you can see that that's 2n. I mean, your first term is 2, your common ratio is 2, T sub n equals T sub 1 plus n minus 1 times d, so you get 200 equals 2 plus n minus 1 times 2, and again you get n equals 100. So there you go, but now we put these two ideas together and express in sigma notation. So what's the sum going to be here? How about what do you want to use for your index? What do you want to use for your variable? I'll tell you why I don't want to use n. Because a lot of the formulas involve n, and then n would change from 1 up to the upper limit. when it's actually the upper limit that you want to do. P. We haven't used P yet. From P equals 1 up to 100 in this case. And what are the terms then? You have to use a formula for the nth term. This ends up being T sub n equals T sub 1, which is 2 plus n minus 1 times 2. But if you simplify, you get the much easier 2n. And the other one is 2n minus 1. T sub n equals 2n minus 1. These are good formulas to remember because this basically is the way to represent an odd number, and this is the way to represent an even number. So if you recognize evens and odds as part of your sequence, you can just go into that. So we have the odd number 2n minus 1 times 2n.
Where's the P?
Exactly. I'm glad you spotted that. Did that intentionally? Did you see that? That was definitely intentional. Because you have to be consistent with what you choose as an index. And right now, P changing isn't going to change this. So you've got to make sure you've got your index in there. Even means breaking out the micro eraser. There you go. Okay. P. There. That's our sequence. Okay? Summation of P equals 1 to 100 of 2P minus 1 times 2P. Now, you could plug that in your calculator and get an answer. I expect you to do this by hand using the things we just talked about. Okay? Can you distribute sigma notation over multiplication? No. But yeah, and we are going to be taking a constant out. You can distribute sigma notation over addition or subtraction. So that's why you want to expand out this bound here. Summation from P equals 1 to 100 of 4P squared minus 2P, right? So it becomes a summation from P equals 1 to 100 of 4P squared minus a summation from P equals 1 to 100 of 2P. And so we get 4, and as Andrew was talking about, taking the constant out, P equals 1 to 100 of P squared, minus 2 times the summation from P equals 1 to 100 of P. Now you whip out those formulas. And I'm going to use my sophisticated, right, if you got it memorized, great. I can admit how maybe you don't have it memorized yet. Exactly. We need a sum of squares, right? So let's look up that formula. We put it right over here, right? There it is, sum of squares. Grab it. Catch it. Yeah, there we go. Boosh. Click. And cut that. And paste it where we need it then, right? See that little formula? We're going to use that. We need the other one too. The sum of the first n, right? You remember that one? Excellent. Oh, I got to go like this. Cut that out. Let's paste that in. And there we go. Now they're ready to go. Now be careful how you use these now. This is going to be 4 times this summation. It's a sum of squares. What goes in for n? 100 times 101 times 201 over 6. And I think we just did that one, right?
Yes.
Minus twice. Now we take this one, 100 times 101 over 2. Which the 2's cancel and we get 10100. Over here, here's the huge one, right? Right, it was 4, it'll be 4/6 of, what was it, 338? 350. Yeah. Will 6 go into that noise? I hope so.
It always does.
It has to. Okay, what do you get when you calculate it all out?
Isn't it? No, it's like times 338.35.
1,000,000.
She already got the.
430.
You wrote 4 6.
It's the same thing.
4 6. Oh, I see. This is 6. This is the number we had before, right? Oh, okay, so it's 4 times that, and so
It's still the same.
1,343,000. 300 and.
300.
Did you subtract off the 101? Oh,
Yeah.
I got some.
you did?
Yeah, I did.
3, 5, 3, 4.
What do we get for the whole thing? Look, check it on your 89.
I did.
Here's the TI-89 check on just this. Summation, left parentheses again, 2p minus 1, 2p, p going from 1 to 100.
Yeah, Joey was right.
And that's the, what do you get from that, Joey?
Joey's right.
1, 343,
300.
300. And you also get it from here too, right?
Yeah.
Excellent. Okay. Now, this I'll accept as a check, and maybe you'll get one of the points. And in fact, if you set it up correctly into here, I'll let you do the rest on your calculator. You don't have to try and do all this by hand, okay? But showing me how you can apply these formulas is key. Yes.
How would you do something if it was like alternating coefficients?
Oh my goodness.
Like it was 1 minus 1 half plus 1 fourth minus 1 eighth.
Yeah, you can express it with the -1 to a power.
Okay.
Yeah, if you see it's alternating sign, we did that trick before with geometrics with common ratios that were negative. In fact, that one you can just use a -1/2 for your common ratio. Instead of its geometric forms. Okay? Better stop there. Go take your cake out in the hall or something like that. Yeah, they have to get neutrified for the chemistry test. Some groups get it together. I think it was a rite of initiation for their new member.